Hello students, welcome to SOURAV sir's classes. The first question is, show that if y and z are independent random values of a variable x, the expected value of y minus z squared is twice the variance of the distribution of x. So first, we need to make a basic set of assumptions. Let us assume that expectation y is equal to expectation z is equal to expectation x is equal to mu, and variance of y, that is sigma y squared, is equal to variance of z, that is sigma z squared, is equal to variance of x, that is sigma x squared, is equal to sigma x squared. Now we need to find the expected value of y minus z squared, which is expected value of y squared plus z squared minus 2yz, which is expectation of y squared plus expectation of z squared minus 2 expectation of yz. Now we can write this further as expectation of y squared plus expectation of z squared minus 2 into expectation y into expectation z, since y and z are independent. Now we also know that expectation y squared is equal to expectation y squared plus variance y, and similarly expectation z squared is equal to expectation z square plus variance z. Thus this can be written as mu y squared plus sigma y squared plus mu z squared plus sigma z squared minus 2 into mu y into mu z. Now since mu y is equal to mu z is equal to mu, and sigma y squared is equal to sigma z squared is equal to sigma squared, we can replace these values as mu squared plus sigma squared plus mu squared plus sigma squared minus 2 into mu, that is 2 mu squared plus 2 sigma squared minus 2 mu squared, which comes out to be 2 sigma squared, that is twice into variance of x. Thus we have proved the answer. The next question is, if x and y are symmetric, show that expectation x by x plus y is equal to half. Now we can write expectation x plus y by x plus y as 1. Since x plus y by x plus y gives 1, so expectation of 1 would be 1. Now this can be written as expectation of x by x plus y plus expectation of y by x plus y is equal to 1. Now since x and y are symmetric, we can combine these two as twice into expectation of x by x plus y is equal to 1, and this comes out to be expectation of x by x plus y is equal to half. Thus proved. The next question is, a fair coin is tossed 4 times. Let x denote the number of heads occurring and let y denote the longest string of heads occurring. Determine the joint distribution of x and y. So first let us write the sample space, like what happens when we toss a fair coin 4 times. it is H, say we get all heads, or we get 3 heads and a tail in the following combination. T, H. Or 2 heads and 2 tails. H, T, H, it is H, T, TH, sorry, TH, or T, double HT. And then we have 3 tails and a single head, so it can be written in the following ways, or rather they can occur in the following ways, and thus we are writing in this way. Or we get all tails, so we get 16 combinations. Let us check once again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So now let us create a table where y goes over here and x over here, and since the coin is tossed 4 times, the longest string of heads you can have is 4 and the minimum you can have is 0. So y can be 0, 1, 2, 3 and 4, whereas x can also be from 0 to 4. 0, 1, 2, 3, 4. Now, given number of heads is 0, so the longest string of heads you will have is actually 0, and that is only possible for this case. So our probability for this is 1 by 16, and for the others is 0, because as you have no heads, you can't have 1, 2, 3 or 4 string of heads. Now the next thing is, given you will have 1 head, 0 strings of head is impossible, and similarly up to 4 heads it's impossible. So these probabilities come up to be 0. Now, given you have 1 head, what is the probability that it is a maximum? It is a maximum at that string of heads. And one more thing, here this would be HT TT rather than an H. So now see, given you have 1 head, what is the longest string of heads you can have is 1. So we'll need to analyze these cases. So the total probability comes out to be 4 by 16, since we have 4 favorable events. Now over here, the rest, that 2, 3 and 4 string of heads, the probability is 0 for them. Now given you have 2 heads, what is the probability that you have a string of just 1? So given you have 2 heads, now let us analyze the cases where we have 2 heads. So we have these 6 cases. Now in how many cases do we have just 1 head? 1, 2 and 3. So this comes out to be 3 by 16. And in the other 3 cases, we get 2 heads continuously, 1, 2 and 3. So this comes out to be 3 by 16, and the probability of getting 3 string of heads and 4 is 0. Now, given you have one head, given you have 3 heads, the probability that you get just a single head at one, just a single string of head is 0. Given you get two heads continuously, you get it in this case and over here. So the probability is 2 by 16, and you get 3 heads continuously. One case is this and the other is this. So 2 by 16 once again, and 4 heads continuously is impossible, so the probability is 0. And given you get 4 heads and the longest string and 4 consecutive heads, the probability is 1 by 16, and rest for 1, 2 and 3 continuous heads is 0. Now if we sum up the probabilities row wise and column wise, we get this as 1 by 16, 4 by 16, 6 by 16, 4 by 16, 1 by 16, and over here 1 by 16, 7 by 16, 5 by 16, 2 by 16, and 1 by 16. And the total probability comes out to be 1.